Lighthouse Scientific Education presents a lecture in the Chemical Reaction series. The topic, Balanced Chemical Equations. Material in this lecture relies on an understanding of the previous lecture, Order in Matter. The lecture begins with a review of the chemical equation, and that includes a review of the companion symbols and terminology. Students comfortable with the chemical equation can jump to the underlying principle of balancing equations, the law of conservation of mass. Then it is on to devising a set of basic rules for balancing equations. These rules are applied to 4 example problems that canvass the common types of equations found in the early study of the process. For many students, these examples will cover the topic in sufficient depth. Some students may want to delve deeper or expand on the logic behind the basic rules. For them, there is a separate lecture, Advanced Concepts in Equation Balancing. On to the review. Chemical equations represent the sentences in the language of chemistry. For example, the reaction of 2 hydrogen molecules plus 1 oxygen molecule produces 2 water molecules. The sentence can also be read 2 moles of hydrogen plus 1 mole of oxygen produces 2 moles of water. A chemical equation is the means of communicating a chemical change. In the previous equation, that change is a chemical reaction involving hydrogen and oxygen. The chemical equation uses symbols and formulas to represent the elements and compounds involved in the chemical reaction. It is the same thing seen in mathematics, where the sentence 3 plus 4 equals 7 can more easily be written with numbers and symbols. Speaking of numbers, there are 2 places in the chemical equation where numbers are found. One is the subscript, the number found in the lower right of an atom. Subscripts give the number of atoms in the compound. Both hydrogen and oxygen are diatomic molecules, that is, there are 2 atoms in each compound. In water, the ratio of hydrogen and oxygen is 2 to 1. The other number is the coefficient. It is found before the compound or element. Coefficients give the number of compounds or elements in the reaction. It takes 2 hydrogen molecules and 1 oxygen molecule to make 2 water molecules. Balancing chemical equations involves inserting coefficients before compounds or elements in the chemical reaction. As for the terminology, there is reactants and products. Reactants are the species present before the reaction. Products are the species present after the reaction. The term species is an inclusive one when used in chemistry. It is a general term for any chemical, be it a compound or be it an element. On the reactant side, the plus means reacts with. There's also a plus on the product side, and that could be interpreted as also produces. In between the reactants and products is a reaction arrow. It means yields or reacts to produce. The single arrowhead arrow is not the only arrow type to indicate the flow of the reaction. The double-headed reaction arrow or the parallel reaction arrows, pointing in opposite directions, means the reaction goes in both directions. This is found with reactions that are in equilibrium. That topic is covered later in the course. Returning to the chemical reaction that produces water, this single arrowhead can be replaced with a double arrowhead or the parallel arrows, since an H2O molecule can break down into H2 and O2. If the reaction strongly goes in one direction, the length of the arrow can be adjusted to visually demonstrate the stronger direction. But often just the single arrowhead is used to indicate the stronger reaction. There are additional terms, such as including the states or phases of the species involved in the reaction. When reactant or product is in a solid state, parentheses S is included after the species. For example, the metal silver is usually found in the solid state. The parentheses S does not have to be placed as a subscript like it is here. Textbooks favor one way or the other, and it's not a significant concern. Learn the style covered in your class. Parentheses L indicates that the chemical of interest is in a liquid state. Water is a good example of that. We can see here one of the major benefits of including a state for the compound. If the compound H2O is followed by an L, then we know that that part of the reaction has to occur between 0 and 100 degrees Celsius. If that were not the case, the water would be found in either the solid or gaseous state. The other major state is the gas state. It is indicated by parentheses G. Elemental hydrogen is always found as a gas. There is one other symbol that comes up regularly, and it is for a compound that is dissolved in water. The compound is said to be in an aqueous solution. The symbol parentheses AQ is used to denote this. The compound copper 2 sulfate readily dissolves into its ionic components in water. The parentheses AQ lets us know that the ions are not locked together in the compound. They have dissociated and are found as solvated ions. This topic is explored much more in depth in the Solution and Solubility lecture in the Water and Solution series. Returning to the formation of water equation, we see that the reactants hydrogen and oxygen are both in the gaseous state. The product H2O is in the liquid state. There is, however, an inherent limitation when assigning states. In this reaction, the formation of water is accompanied by a large release of energy. Much of the water is found in the gaseous state. The decision of whether to include the L or the G as a state is a difficult one and dependent on the conditions of the reaction. It is not a distinction that a beginning chemistry student will usually have to make. There are more symbols used to communicate change in a chemical equation. Some reactions produce a gas that escapes into the atmosphere. To demonstrate that, an upward pointing arrow is added next to the gas. Alternately, sometimes a reaction taking place in a solution produces a solid that precipitates or sinks to the bottom of the reaction vessel. This is indicated with the addition of a downward pointing arrow. Reactions that produce or consume heat are often accompanied by the Greek symbol delta, which means change. The delta symbol is usually included on top of the reaction arrows, as is the presence of a catalyst. Catalysts are involved in speeding up a reaction, but are not consumed in the process. They are unaltered in their reaction. Here the addition of the catalyst platinum metal is indicated by the element symbol over the arrow. That sums up the major symbols and terminologies used in chemical equations. The degree to which the symbols need to be included with a reaction is dependent on circumstance and accepted practices. Know what is required of you. The balancing of chemical equations follows from the law of conservation of mass. That law states that in an isolated system, the total amount of matter remains constant. Another way of saying that is that matter cannot be created or destroyed. It can change form. Bringing up the formation of water equation, along with a cartoon representation of atoms involved in the reaction, shows that the mass of the reactants is equal to the mass of the products. Conservation of mass. A more succinct way of putting that is that the atoms in the reactants are the same atoms as in the products. The chemical reaction is really just a rearrangement of how atoms are bonded. That will also include ions. Balancing the chemical reaction is nothing more than making sure that all the atoms in the reactants are in the products, and vice versa. A set of rules has been established that puts order to the process of balancing chemical equations, but they are just rules for getting the outcome. Rules are not how the reaction proceeds. It is important to separate out the process of balancing chemical equations from the actual chemistry of the reaction. There is absolutely no connection between how we balance chemical equations and the actual chemistry of the reaction. The rules are a bookkeeping mechanism to get a balanced equation. A different set of rules should also get the same balanced equation. As such, balancing chemical equations is a bit of an art. The more chemical equations that a student solves, the easier the process of solving equations becomes. And students will need to know how to balance the chemical equation moving forward in their study of chemistry. The process begins by writing out the chemical equation, write out the reactants and products. It's helpful to leave a little room in front of the compound so that coefficients can be added. Include a reaction arrow, and if asked for, include the states of matter. Of fundamental importance, once the reactants and products are written out in the equation, the compounds will never change. That is, never change subscripts in the compounds. It might seem that an easier way to balance the number of atoms is to change subscripts, but that changes the compounds. They will no longer be the chemicals given in the reaction. Changing subscripts is an automatic failure of this process. Returning to the equation, count the total number of each atom type for reactants and for products. Additionally, start a tally or a count for each atom type on the reactant side and a tally for each atom type on the product side. 2 tallies. Remember, the number of an atom type in a compound in a chemical reaction is gotten by multiplying the subscript of the atom by the coefficient of the compound. Often, a table is used to keep track of the reactant tally and the product tally. The equation is balanced when the 2 tallies are equal. Balancing the chemical reaction is nothing more than making sure that all the atoms in the reactants are in the products. As a bit of a heads up, if there's a polyatomic ion that is the same on both sides of the reaction, treat it as a single entry in the tallies. That is, it is not necessary to break it down into individual atoms and add those to the count. Example 4 covers this more in depth. Step 3 is to balance atom types, one at a time, by adjusting the coefficient in front of a compound that contains that atom type. This is the art of the process, and best understood using example problems. A helpful tip for this step is to balance single atom type compounds last. Compounds such as N2, O2, and H2 have only one type of element in the molecule. We will see this tip play out in the example problems, and its logic further demonstrated in the companion lecture, Advanced Concepts in Equation Balancing. If a coefficient is changed, then the count of atoms from that compound has changed. Step 4 is to recount atom types in compounds where the coefficient is changed. Change the tally to reflect the change in the number of atoms. And in most chemical equations, steps 3 and 4 are repeated with other atom types until the tally of atoms in the reactants is equal to the tally of atoms in the products. This makes more sense if more than one compound has a change in its coefficients. Almost there. Once a balanced equation has been obtained, the last thing to do is to verify that the compound coefficients are in the lowest whole number ratio. Reduce by a common factor if necessary. For most equations that are balanced using this set of rules, the coefficients obtained will be in the lowest whole number ratio, and there will be nothing to do with this step. Not all, however. Here's a hypothetical example that just contains the coefficients of a balanced equation. The coefficients will need to be reduced because the ratio of coefficients is not the lowest whole number ratio. These are all even numbers, and if each value were divided by 2, division by a common factor is how reduction is made, a new ratio would be produced. That is the same overall ratio, but with lower whole numbers. The concept is explored in more depth in the example problems and in the companion lecture, Advanced Concepts in Equation Balancing. On to the examples. The process begins by writing out the chemical equation, and that equation is elemental zinc reacts with hydrochloric acid to form zinc 2 chloride plus elemental hydrogen. These are the compounds in the equation. They will never be changed because we will never change the subscripts. Using the equation, count the total number of each atom type in the reactants and in the products. That is, start a tally for each atom type on each side of the reaction. There are many ways to arrange a tally between atoms in the reactants and the products. We will use a vertical table with the first column, the tally of reactants, and the last column, the tally of products. The middle column is for each atom type in the reaction. According to the equation, that would include zinc, hydrogen, and chlorine. The term chloride could have been used here since chlorine is found in its ionic form. We will stick with its elemental name. Are there any additional elements in the chemical reaction that we have not included in the table? No, that's all of them. Now we count them up. On the reactant side, how many zincs do we see? There's just the one, since there's no subscript indicating additional atoms. Include a 1 in the reactant column next to the zinc symbol. And the hydrogens, how many are there? Again, we see just the 1. The atom remaining in the reactant column is the chlorine, and there is only one of those. The atoms of the reactants have been tallied. On to the product side. Beginning with zinc, we see that there's only 1 zinc. That is added to the tally on the product side. Keeping the order of the column, how many hydrogens are there on the product side? That subscript 2 tells us there are 2 hydrogens. And finally, how many chlorines? Again, the subscript 2 tells us that there are 2 chlorines. The product tally is finished, and a comparison of the tallies on the reactant and the tally on the product side show that they are not equal. As written, this is not a balanced equation. Moving to step 3, we attempt to balance this equation by changing the coefficients in front of the compounds, and we do so one atom at a time. But which of the atom types that are not balanced should we attempt to balance first? A look at the tally shows that the hydrogens are not balanced. Neither are the chlorines. The decision of which atom to balance first should include using the tip that says balance single atom type compounds last. Is either the hydrogen or the chlorine found in a single atom type compound? Yes, H2 contains only hydrogens, so balance the hydrogens last. That leaves the chlorine as the first atom type. The next question to ask is whether to adjust the coefficient in front of the compound with the chlorine in the reactants or in the products. The tally shows the product sides who have more chlorines than the reactant side. If we want to balance chlorines, then we need to increase the chlorine on the reactant side. What whole number coefficient could be added in front of the HCl to boost the count of chlorines to 2? Remember, the number of atoms in a compound of a chemical reaction is gotten by multiplying the subscript of that atom by the coefficient of the compound. The subscript of the chlorine in HCl is an implied 1. Therefore, 1 times 2 will give 2 chlorine atoms. If the coefficient in front of a compound is changed, there is a need to recount the atom types in that compound. A recount is only needed for atom types in that compound on that side of the reaction. The recount should only reflect the change in atoms due to the change in the coefficient. There are now 2 HCl's. Both counting of the hydrogen and chlorine on the reactant side needs to be adjusted. Starting with the hydrogen, multiplying the coefficient of 2 by the implied subscript of 1 gives 2 hydrogens in the reactant tally. Same math is done with chlorine, giving it also a 2 in the reactant tally. Initially, there were 2 atom types that were not balanced. A repeat of steps 3 and 4 might be needed to balance the other atom type, but a direct comparison of the 2 tallies shows that each side has the same number of atoms for each atom type. The equation is balanced, and there is no need to change any other coefficients. The hydrogens were balanced in the same step that balanced the chlorines. Are we done? Maybe, but we still need to verify that the compound coefficients are in the lowest whole number ratio. And pulling out just the coefficients and including the implied ones, we see that this set of whole numbers cannot be reduced to a smaller set of whole numbers. Why this step is here is that sometimes in the balancing process a different ratio is found. For example, the student might correctly balance the equation but end up with this set of coefficients. The ratio of the coefficients is the same. A tally of both sides would yield equal amounts of atoms on the reactant and product sides. But this is not the lowest whole number ratio. Each of these values can be reduced to a smaller whole number by dividing the whole lot by 2. It's important to remember that to keep the ratio found with the balancing, each coefficient must be divided by the same number, and that in the end, the new lower set must also be whole numbers. One down. The next example has the equation silver 1 iodide plus sodium sulfide produces silver 1 sulfide plus sodium iodide. In the types of chemical reactions lecture, this reaction would be classified as a double replacement. This time we will act as if there was a requirement to put the states of matter. At this point in their study of chemistry, most students are not asked to know all the states of matter for all compounds. Given a reaction like this, it might have been pointed out that the reactants were dissolved in water, meaning that they are in the aqueous phase. It might also have been noted that the silver 1 sulfide is a solid and precipitates out of solution. Compounds are never changed because we never change the subscripts. On to counting up the atom type for the reactants and products and putting them into a tally. The first step with the tally should be to identify the atoms in the reaction. All of the atoms in this reaction are in their ionic form, but we will still call them by their element name. There is silver, Ag, iodine, sodium, and sulfur. Starting with the reactant side, how many silvers are there on this side of the equation? Just the one. How about iodine? Again, just the one. What about sodium, Na? That 2 subscript tells us that there are 2 sodiums. And sulfur? There is only one of those. On to the product side. How many silvers are there? The 2 subscript tells us that there are 2 silvers. And sulfurs? There is 1. Sodiums? 1. And iodide? That 2 is just 1. The tally of atoms in the reactant products is complete, and a comparison shows that they are not equal. As written, this equation is not balanced. We need to balance atoms one at a time by adjusting coefficients in front of some or all of the compounds. A look at the tally shows there to be an uneven number of silver atoms and sodium atoms. Which atom should we balance first? A look at the tip with this step does not help since there is no single atom type compounds with these elements. So, which atom type should be balanced first? Generally, one looks at the equation and chooses the easiest atom type to balance. Unfortunately, this particular suggestion is not very helpful since both atom types look equally as difficult or as easy to balance. Let's just take the top one, silver. The next question is whether to adjust the coefficient in front of the silver compound in the reactants or in the products. There are more silver atoms in the products, so balancing will come by increasing the coefficient on the reactant side. There is an implied 1 subscript on the silver. What coefficient is needed that when multiplied by the subscript of 1 gives a value of 2? That, of course, is 2. Changing the coefficient means recounting the atoms in the compound silver 1 iodide. The recount involves atoms that have been changed by the change in the coefficient. That's both the silver and the iodine. They have implied subscripts of 1. Multiplying the subscript of 1 by the coefficient of 2 gives a new reactant tally for the silver and iodine of 2. With this change, is the equation now balanced? In a comparison of tallies, we see that the equation is not balanced. By changing the coefficient to get the silvers to be balanced, we have taken the iodines out of balance. This is not a mistake. It is a natural part of the process. The only thing to do is to keep at it and that means steps 3 and steps 4 need to be repeated for a different atom type. Step 3 has us change the coefficient on another compound to get a different atom type in balance. We could do this for the iodines or return to one of our first options, the sodium. The question becomes, should we change the coefficient in front of the sodium on the reactant side or the product side? There are more sodiums on the reactant side, which means the product side needs to be increased. But by how much? To be equal, the product side tally of sodium needs to be a 2. What coefficient, when multiplied by the subscript value of 1, yields 2 sodiums? That would be 2, which brings up step 4, recounting the atoms in the compound with the change to the coefficient. Both the sodium and the iodine have implied subscripts of 1. When the 1 is multiplied by the new coefficient of 2, the product tally of the sodium and the iodine become 2. Is this equation balanced? According to the comparison of tallies, it is. Almost there. The last step is to verify that the compound coefficients are in the lowest whole number ratio. Separating them out and bringing them to the front, we see that the ratio is indeed the lowest whole number ratio. A point of fact is that if one or more of the coefficients is a 1, then the ratio has to be the lowest whole number ratio. On to the next example. And this equation looks like it might be relatively easy to balance since there are only 3 compounds in total. In fact, there are a few new concerns to deal with in balancing this equation. The equation has potassium chlorate decomposing in the presence of additional heat, note the delta sign, into the salt potassium chloride and molecular oxygen gas. Compounds in this reaction are set because we never change the subscripts. If this problem asks for states of matter, the student might remember that potassium chloride is a salt and a solid, and that the molecular oxygen is a gas. Potassium chlorate would probably need to be looked up to identify it as a solid. Using the equation, count the total number of each atom type for reactants and for products. Some classrooms and textbooks use a horizontal tally. We will stay with the vertical one. It doesn't really make a difference. Atoms in this reaction include potassium, chlorine, and oxygen. For a count, on the reactant side, there is 1 potassium and 1 chlorine, and there are 3 oxygens. On the product side, there is 1 potassium and 1 chlorine. As for oxygen, there are 2 of those. Comparing the tally shows that, as written, this is not a balanced equation. There are more oxygens on the reactant side than there are on the product side. So, it is on to balancing that atom type by adjusting the coefficient in front of a compound. But which one? Since there are 3 oxygens in the reactants and 2 in the products, a larger coefficient in the products is needed. But what coefficient times the product oxygen subscript of 2 will give a value of 3? That would be a coefficient of 1.5, but coefficients are limited to whole numbers. So what gives? There are a couple ways to approach this quandary, and they are both discussed in detail in the companion lecture, Advanced Concepts in Equation Balancing. Here we will stick with the way that only puts whole numbers in for coefficients. What that ultimately means is that the oxygen count on both sides of the equation will have to be changed. It's not as difficult as it sounds. It's actually quite similar to the process of getting a common denominator when adding fractions. The analogy being that the 3 and the 2 are like denominators of 2 fractions. The common denominator for those 2 is called the lowest common multiple, or LCM. The LCM here is the smallest number that can be divided by a 3 and by a 2. That is the number 6. So 6 is the number that the 2 count on the product side needs to be converted into. Once that is done, The count of 3 on the oxygens on the reactant side will also need to be converted into a 6. That way the count on both oxygens is equal as required by a balanced equation. First to the product oxygen. To get the coefficient for a molecular oxygen, the question is what coefficient value times the subscript value of 2 gives 6. And that, of course, is 3. Insert the 3 in front of the O2. Changing coefficients means a recount of atom types in the compound with the changed coefficient. Well, this is a single atom type compound, and the coefficient of 3 is there to give a count of 6 for oxygen. A look at the tally now shows the oxygen on the product side to have a larger count. The potassium chlorite needs to have a larger coefficient to balance the oxygen, so steps 3 and 4 are repeated. The question for this compound is what coefficient times the subscript of 3 on the oxygen will give a value of 6. That is a 2, which is inserted in front of the compound and requires a recount of the atom type in that compound. All 3 atom types are in this compound, and all 3 counts will change. Starting with the oxygen, since it is the reason for the change, 3 times 2 is 6. There are 6 oxygens on the reactant side, as was the goal. Both potassium and chlorine have an implied subscript of 1, so coefficient times subscript will give a count of 2 for potassium and 2 for chlorine. Comparing tallies shows that changing the coefficient on the potassium chlorate has the effect of unbalancing the potassium and the chlorine. Balancing equations sometimes has a ping-pong feel to it. So it's back to steps 3 and 4. The count on potassium and chlorine on the product side needs to be increased. But which atom should we choose? It's not really a choice since they are both in the same compound on the product side. Let's say we are balancing the potassium. What coefficient times the subscript on the potassium of 1 will yield a value of 2? Yes, 2. And with a coefficient change comes a recount. The compound has both a potassium and a chlorine atom. A coefficient of 2 was added to give the potassium a count of 2. The same math of coefficient 2 times subscript gives chlorine a count of 2. Comparing the tallies shows that the reactants and products have equal count of atoms, and the equation is balanced. What remains is to verify that the compound coefficients are in the lowest whole number ratio. Pulling the coefficients out and down shows the ratio to be 2 to 2 to 3. While there are no ones that automatically define the ratio as lowest, there is no whole number that can divide each coefficient and produce a set of whole numbers. The equation is therefore balanced. One last example, and it deals with polyatomic ions. It is a neutralization reaction. It is an acid-base reaction that produces a salt and water. The aqueous base sodium hydroxide reacts with aqueous sulfuric acid to produce the salt aqueous sodium sulfate and water H2O. Step 2 in the process involves counting the total number of each atom type for the reactants and for the products. A tally is started for each atom type on each side of the reaction. The atoms involved in the reaction are sodium, oxygen, hydrogen, and if we want, we can include the sulfur, which is found in the sulfuric acid. However, a closer look at the reaction shows that the polyatomic ion sulfate is present in its entirety on both sides of the reaction. The sulfate is unaltered in the reaction, and we can treat it as if it was a single entity. In this tally, the sulfur can be replaced with sulfate. It will be counted just like an atom type. It's important to note that those oxygens that are not in the sulfate will still need to be balanced. One benefit that can be seen directly from using the polyatomic ion in a tally is that the oxygens in the ion do not need to be counted with the oxygen atoms in the other compounds. it simplifies the entire balancing process. A deeper look at counting polyatomic ions as a whole can be found in the companion lecture, Advanced Concepts in Equation Balancing. On to the count, and starting with the reactant side and the sodium. How many sodiums are there on the reactant side? Just the one. And oxygens? We do not need to include the oxygens in the sulfate. The single oxygen in sodium hydroxide is a count of 1. What about the hydrogens? Well, sodium hydroxide has 1 hydrogen, and sulfuric acid has 2 hydrogens. The hydrogens in the sulfuric acid are not part of the sulfate ion and need to be counted. The tally is 3 hydrogens. Now, what is the count of the sulfate ion on the reactant side? There appears to be just one of those polyatomic ions. If there were more than one sulfate ion, there would be parentheses around the entire ion, followed by a subscript value indicating the number of ions. No parentheses here, so the value is 1. Moving on to the product tally, how many sodiums are there in sodium sulfate? The subscript 2 tells us that there are 2. Keeping with the order of atoms in the table, how many oxygens are there on the product side? The oxygens in the sulfate ion are not counted with the oxygen in water, so there is only 1 oxygen. What about hydrogens? Again, that takes us to water, which has 2 hydrogens. And finally, counting the sulfate ion. There are no parentheses around the ion, implying that there is just 1 sulfate on the product side. Comparing the reactant and product tally shows the count to be unequal. Some balancing is in order, but with which atoms? The tip for this step is to balance the single atom type last, but there are no such compounds in this equation. The tally shows that the sodium and hydrogen have unequal counts. Hydrogen has a count of 3 to 2, similar to what was found with oxygen in the previous problem. Balancing those oxygens was not an easy process, and if we were to start the balancing of this equation with the hydrogens, it would be a difficult start. Looking at the sodium count, we see that it does look quite a bit more manageable. It is an unwritten rule in balancing equations that one balances the easiest to balance atom types before the harder to balance ones. The logic is that sometimes the process of balancing the easier atoms has the effect of simplifying the balancing of the harder ones. Sodium it is then. The product side has more sodium ions than the reactant side. The reactant side needs to have a new coefficient in front of the sodium hydroxide to increase the sodium count. What coefficient value times the implied subscript of 1 of the sodium will give a value of 2? It is, of course, 2. Changing the coefficient means recounting the atom types in that compound on that side of the reaction. There are 3 different atom types in the sodium hydroxide. The purpose of the 2 coefficient was to get the count on the sodium to be 2. Both the oxygen and the hydrogen have implied subscripts of 1. Multiplying 1 times the coefficient gives 2 oxygens and 2 hydrogens from this compound. That gives a count for oxygen of 2. It's a bit more complicated for the hydrogen. Those 2 hydrogens from the sodium hydroxide need to be added to the 2 hydrogens in the sulfuric acid to give a count of 4 hydrogens on the reactant side. The tally comparison shows there still to be an uneven atom type count. Another round of steps 3 and 4 is needed. The atom types that need balancing are the oxygen and hydrogen. A look at the tallies shows the reactant side to have more of each of these atom types than the product side. Therefore, a compound on the product side needs to have a coefficient increased. We can focus on balancing either the oxygen or hydrogen because the balancing is going to go through water. Let's look at oxygen. What coefficient on water, when multiplied by the implied subscript of 1 on the oxygen, gives a value of 2? That is 2. And if the coefficient is changed, a recount of atoms in that compound is needed. Water has oxygen and hydrogen atoms. The coefficient of 2 in front of the water is there to give the oxygen a count of 2. The total count of product hydrogens is the coefficient 2 times the subscript 2 for a value of 4. Comparing the tallies shows all atoms to have the same count. The equation is balanced. Notice that the count of sulfate ion remained unchanged in the balancing. This supports our decision to group it whole as an atom type. The last step is a check of the coefficients. The 2 to 1 to 1 to 2 ratio is the lowest whole number ratio. Any ratio with a 1 fits that bill. These 4 examples cover most of the issues that come up in balancing chemical equations at this level of chemistry. For most students, this is as much of the lecture as they need. For those who feel they need a deeper understanding, or for those students who will be expected to solve more advanced equations, move over to the companion lecture, Advanced Concepts in Equation Balancing. Recapping the lecture. A chemical equation is the means of communicating a chemical change. Reactants are the species before the reaction. Products are the species after the reaction. Species is a general term for any chemical. Balancing chemical equations follows the conservation of mass. In an isolated system, the total amount of matter remains constant. There is no set way to balance the chemical equation. Rules are not explanations of how reactions proceed, but they are a helpful guide. Begin by writing out the chemical equation, reactants and products. Never change the subscripts. Count total number of each atom type for reactants and for products. Start a tally for each atom type on each side of the reaction. The tally is how we keep track of the changes made in balancing the equation. Balance atom type, one at a time, by adjusting coefficients in front of a compound. This is the art of the process. If the coefficient is changed, recount atom type in that compound. Steps 3 and 4 are repeated as needed. That is, until the tally in the reactant and product sides are equal. Finally, verify that the compound coefficients are in the lowest whole number ratio. And that concludes the lecture on balancing chemical equations. This is a subject that students greatly benefit from following the procedure.